Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over an exercise where we're going to check the conditions of the integral test. But this time the given infinite series have a very special form. In one case we have 1 over n to the power of 1.001. Another one is like 1 over n to the power of 0.9. So it's of the form like 1 over n to the power of p. So we call these series as like p series, and the convergence of the p series can be shown by using the integral test. So you will see that we're going to check the conditions of the integral test to deduce something about the convergence of the given p series. All right, let's get started.
All right, so let's recall what the integral test is all about. Here's a description of that. So we have three conditions to check. One is f being positive, two, f being continuous, three, f being increasing for x is greater than or equal to 1. And then we'll look at the improper integral in terms of its convergency. And if it's convergent, then the infinite series is convergent. And if it's divergent, the infinite series is divergent. Okay? But again, before we apply the integral test, we have to check all three conditions to be satisfied. And for that, I just list them down here. So we're going to check f being positive first. Well, but before doing that, why don't we construct an being equal to fn, and that is equal to n to the power of 1.001. So that allows us to grab f of x to be this for x is greater than or equal to 1. Okay, if x is greater than or equal to 1, you're talking about like 1.001 power of a positive number, and that's positive. So this is immediate that f is a positive function. And is f continuous? Well, as long as x here is not equal to 0, so that you're not dividing by 0, f is continuous. Okay, so here f is continuous because 1 is continuous, bottom is continuous, and the quotient is continuous because x is not allowed to be 0. So we're safe. Okay, and how about f is decreasing? Well, we're going to use the first derivative test. We're going to use calculus 1 to prove that. But before we do that, why don't we rewrite this expression as an exponent? So like exponential expression, so x to the power of negative 1.001, so that we can use the power rule rather than the quotient rule to take the derivative of f. Okay, so f prime is going to be the power down times, we're subtracting 1 from the power, so that makes it minus 2.001. In other words, it's equal to x to the power of 2.001. Okay. Well, top is negative and the bottom is always positive. So this guy is always positive and this is always negative. So that makes f prime to be negative. Okay, so when f prime is negative, then f is a decreasing function. So I have to put a check mark right here. Okay, so now I have to go back and check look at the integral from 1 to infinity of f of x dx. Okay, let's just do that real quick. All right, since the integral we're after is the improper integral, and since we haven't integrated the integrand yet, so why don't we look at the indefinite integral first and integrate it, and then go back to the improper integral. So to integrate this function, I'm going to write this as x to the power of minus 1.001 so that I can use the power rule for integration, which essentially says that you're going to add 1 to the exponent and divide by the new exponent. Okay, let's simplify this. That is x to the minus 0.001. I'm not using any decimals at this point. I'm trying to get the exact expression of this. Okay, so minus 0.0001. Okay, and that is me writing this as a reciprocal, so x to the power of 0001. And instead of this, So this is 1 over 1000. I flip it over together with its minus sign, so it's negative 1000 divided by x to the power of 0.001. All right, so I don't need to worry about integrating constant, because I'm going to use the result here towards evaluating the improper integral here. So this integral essentially is equal to, there we go, negative 1000 divided by x to the power of 0.01, 1 from infinity. So we don't really plug in infinity as a number, so you write this expression in terms of limits. So this is the limiting expression. So I'm going to use limit b approaching infinity, negative 1000. So now I'm plugging in b instead. Okay, 0.01. That's me putting the upper limit in. Okay, and then minus, you plug in the lower limit. So there's another minus sign over there, 1000 divided by 1, essentially. Okay. Let me clean the right-hand side so we can continue from here. Okay. All right. So here we go. I'm going to pass the limit. When you pass the limit here, so b is a very, very large number, and you're taking a positive power of that. It doesn't matter how small it is, but b is going to be very, very large, and it's the positive power, so it's going to be a huge number. And you're dividing negative 1000 by a huge number, so this term is going to be 0. Okay, when you pass the limit, and as you see that, by the way, I put I forgot to put another minus here. Okay, so please, there's a typo here because it's minus 1 plugged in to this expression here. That makes it negative 1000. Okay, so that takes you to 1000, and 1000 is a finite number. So then this is a finite number. And going back to this expression here, that I can say like this is convergent. Okay, so is the infinite series. Okay, so I can go ahead and then write here that this series is convergent. Okay, that takes care of part A. For part B, I'm going to apply the same strategy. Okay, so I'm going to go back here. This time, the power is different. The power is different. So let me just show it here. It's point, let's see, what was that? It's 0.9. Okay, here we go, 0.9. Okay, so here, then I have 0.9. And here I have 0.9. I'm intentionally doing this because we're going to essentially do the same type of process. So it's minus 0.9. Okay, so let's do the f prime calculation here from scratch, and let's check all three conditions again. But again, this is very similar. So you have x to be greater than or equal to 1. And x to the power of 0.9 is going to be positive. 1 over that is going to be positive. So this is check marked. And same as the continuity argument in the previous part. This is part B, by the way, right? So now I have 1, the top to be continuous, the bottom to be continuous. So the quotient is continuous as long as x is not equal to 0, but we're safe because x is greater than or equal to 1. So I can put a check mark here. Okay. The only different thing in the analysis here is the differentiation here and integration in the next step. So let's just do that. We already put this quotient in the form of reciprocal, right? Like it was in the reciprocal form, but we put it in the exponential form. So the derivative is going to be what? Minus 0.9 x to the power of minus 0.9 minus 1. Okay, so that's minus 0.9. This is x to the power of negative 1.9. Take the reciprocal, go back to the original quotient form. As you see that this is always positive, right? And this is always negative. Okay, so this whole thing is negative. Okay. So f prime is decreasing. So sorry, f prime is negative. So f is a decreasing function. Okay. So why don't we go ahead and then look at this integral back here. So I'm going to erase this and then come back to this. All right, here we go. We're checking this improper integral, but first we look at the indefinite version of that. So let's rewrite this with the exponential form. And this is just for us using the power rule for integration. So x to the point minus 0.9 plus 1, we add 1 to the exponent and divide by the mu exponent. And that is x to the power of 0.1 divided by 0.1. Okay. 0.1 is 1 over 10, right? So if you flip that over, it's 10 times x to the power of 0.1. Okay. All right, since we're done with the integration, I can go back. Again, I don't need to put an integrating constant here because I'm going to use this result towards here. So because the ultimate goal is to evaluate the improper integral. All right, so 10 x to the power of 0.1, 1 to infinity. But infinity limit is going to be written in the limiting sense. Okay, 10 b to the power of 0.1 minus 10 times 1 to the power of 0.1. Any power of 1 is 1, so it's just 1. Okay? So here we go. So we have to pass the limit. Okay? So b approaches infinity. So you're talking about a positive power of infinity. Well, unfortunately, this is going to be infinity. So this is just a constant 1. Infinity minus 1 is still a big number. A big number minus a finite number is a big number, right? So this is diverging to infinity. Okay. So is this. All right, we can go back and conclude that since the integral is divergent, the infinite series must be divergent. So here we go. So this guy is divergent. So is this. So I go ahead and write here that this series is divergent. Okay. So the given series, by the way, are very special series. We call them like P series. So we in fact have a special test. We call it like P series test to conclude about the convergence or divergency. But the proof of the P series test relies on the integral test. So, but I reserved one example in this section. There's going to be another video that we use the P-series test to directly conclude that these series, like the first one is convergent and the other one is divergent. So I would totally recommend you to check the P-series test after you're done with the analysis, after you're done understanding the mathematics here. And but with the P-series test, you can get those conclusions in just one shot. Okay. All right, I think that ends the video. Thanks for watching. I'll see you in another video. Bye.